In this video, we'll learn about the kinematic equations. We'll learn what they are, where they come from, and how to use them. First of all, the kinematic equations take most of what we already know about motion and combine them together into a set of four equations. The basic building blocks of the kinematic equations are the acceleration equation, A equals delta V over T, the equation for delta V equals Vf minus Vi, the velocity equation, velocity equals delta x over t, or displacement over time, and that concept where the area under the line in a velocity time graph is equal to the displacement of the object. Basically, all of those things get combined together to make these four kinematic equations. All four kinematic equations are based around five variables. We have an initial velocity and final velocity, so there's two different velocities, beginning and end, displacement, time, and acceleration. Kinematic equations assume that there is acceleration taking place and that acceleration is constant. If there were no acceleration, you wouldn't be able to use the kinematic equations. Or if that acceleration was variable, it speeds up slowly at first and then it speeds up at a faster and faster rate, you couldn't use the kinematic equations. It has to be constant acceleration. So objects can speed up or slow down, but they have to do so at a constant rate. Each of the four kinematic equations will leave out one of the variables from the list. So again, if we go back to the list, there are five variables there: initial velocity, final velocity, displacement, time, and acceleration. Every kinematic equation has initial velocity in it. There'll be one that doesn't have final velocity. There'll be one that doesn't have displacement, one that doesn't have time, and one that doesn't have acceleration. Let's start with the one that has no displacement, no delta x. It is final velocity equals initial velocity plus acceleration times time. Vf equals Vi plus At. This equation is just a rearrangement and a substitution in the acceleration equation. Let's take a look at how it works. This equation right here is the acceleration that I taught you, delta V over T, or change in velocity over time. But we know that change in velocity, delta V, is equal to Vf minus Vi. So the first thing we do is we replace this delta V with that expression, Vf minus Vi. So again, the first thing we're doing is just a substitution. We're replacing delta V with Vf minus Vi. What that gives us is this equation. Acceleration equals Vf minus Vi over T. Now all we got to do to get to this format is rearrange that equation to solve for Vf. First thing I do is multiply both sides by T. When I do that, I get Vf minus Vi over here on the right-hand side, and I get A times T over here on the left. And then to get rid of the Vi, because I'm subtracting Vi, I add Vi to both sides, which gives us our final form. Vf equals Vi plus At. One of the more simple kinematic equations to derive. You just substitute Vf minus Vi for delta V, and then you rearrange the equation so it says Vf equals. This is your no displacement kinematic equation. The next one we'll look at is the no acceleration kinematic equation. It is delta x equals Vi plus Vf divided by 2 times t. I do want to point out sometimes you see it with parentheses around the Vi plus Vf over 2. So like this. So they can get rid of the multiplication sign. So you don't mistake it for displacement. It's not really good to have x's in equations when x is one of your variables. So sometimes you'll see this whole expression in parentheses and the t on the outside. Sometimes you'll see it written as delta x equals 1/2 VI plus VF times T. Again, just to get rid of that time sign and make it more linear, I would assume. But all three are the same thing. All three are the same equations. So whatever form you're given, you're given. Again, this is a simpler one to derive. This is just a rearrangement of the velocity equation. This is the velocity equation that we learned. Velocity equals delta x over t, or velocity equals the displacement divided by time. First thing we do is rearrange it so we solve for delta x. To do that, we multiply both sides by t. That leaves us with delta x equals v times t. This number right here is really an average velocity. It's really VA. It's an average velocity, and that is because it's calculated over a period of time. Any velocity over a period of time would be an average velocity. Another way to calculate an average is to add up all your values, all the numbers you have, and divide by the number of values, the number of numbers. That is what this is. We have two velocities that we're adding together, VI and VF, and because there's two of them, we divide by 2. Basically, this is also VA. This is another way of finding an average velocity. Add your initial and your final together and divide by 2. So this is just the velocity equation rearranged to solve for delta x with the average velocity replaced with a different average velocity, VI plus VF over 2. The last two kinematic equations are a lot harder to derive, and that's because this one is based on the area under the graph, on a velocity time graph, under the line on the velocity time graph. And the other one's a more complicated substitution of a kinematic equation, not one of the basic ones. So let's start with this. This is the no final velocity equation. The no final velocity equation is displacement equals initial velocity times time plus 1/2 acceleration times time squared. Again, this is based on the area below the line on a velocity time graph. This complex mess of letters and numbers is how it works. This is a velocity time graph. That's the line on my velocity time graph, the red one. I know the displacement is the sum of this blue and orange part. The blue part is VIT, the orange part is 1/2 AT squared. Let me show you how it works. This is a rectangle, and the area of the rectangle is its height times its base, or VI times T. The area of the blue part is VI times T. That's where the VI times T comes from. The area of the triangle would be 1/2 the height times the base. 1/2 the height times the base. 1/2 the height, VF minus VI is the height, times the base, T. Now here's the problem with leaving it like this. This is the no VF equation, so we can't leave VF in here. So what we do is rearrange the acceleration equation so it says VF minus VI. To do that, we just multiply both sides by T. That'll give us AT over here and VF minus VI over here. Since AT equals VF minus VI, we can take this part right out and replace it with AT. And if you do AT times T, you get AT squared. So that second part is just the area of that orange triangle. That's probably the most difficult one to comprehend because you have to understand that graph to really get it. This is the final kinematic equation, Vf squared equals Vi squared plus 2a delta x. This is the no time equation. The final velocity squared is equal to the initial velocity squared plus 2 times acceleration times displacement. This is a derivative of the second kinematic equation. This one right here is derived from this equation right here. Here's how it works. We start with this equation. And our goal is no time. We got to get time out of it. So we got to get rid of t. So what we do is we take the acceleration equation again, and it keeps popping up. All these are about acceleration. Acceleration equation again, solve it for t. So you multiply both sides by t first, you get at equals Vf minus Vi, and then you divide both sides by a, and that's what you get. T equals Vf minus Vi over a. That allows us to get rid of the t and replace it. Now we got to simplify that mess. Vi plus Vf times Vf minus Vi is Vf squared minus Vi squared. And then 2 times a for the denominator. Now all we got to do is solve this thing for Vf squared. So the first thing I do is I multiply both sides by 2a. That gives me 2a times delta x equals Vf squared minus Vi squared. Then I get the Vf squared by itself. I just add Vi squared to both sides, and I have my kinematic equation. We got a lot in there about how they're derived. And if you're in a CP class, it doesn't really matter how they're derived. It probably doesn't even really matter that you know how they're derived. If you're in an honors class, again, probably the same. You may be asked to explain something, who knows. But if you're in an AP class, you're stuck with whatever equations they give you on the AP exam reference sheet. So you got to be able to make some equations sometimes. And so being able to derive those equations is the key to making them for yourself. There's all four. Again, Vf equals Vi plus At. That's the one that has no displacement, no delta x. Delta x equals Vi plus Vf over 2 times t. That is the no acceleration equation. Displacement equals initial velocity plus final velocity divided by 2 times t. Delta x equals Vit plus 1/2 At squared is the no final velocity equation. Displacement equals initial velocity times time plus 1/2 acceleration times t squared. And then finally, Vf squared equals Vi squared plus 2a delta x is the no time equation. Final velocity squared equals initial velocity squared plus 2 times acceleration times displacement. So there you have it. Those are the four equations, where they come from and what they're used for. You get 3 variables, you're missing the fourth, you try to solve for it. There's some problem solving that comes into play in determining which equation you're going to use. So that's what makes this more difficult than the more basic kind of motion calculations. Let's take a look at how some of this works. So we start off with a car. That car is accelerating at a rate of 12 meters per second squared. Accelerates 12 meters per second squared, that's A, for 2.5 seconds. Seconds is time. If the car has an initial velocity of 7.1 meters per second squared, that's Vi, how far, delta x, will it travel? So again, I'm still doing my same uniform problem solving approach. I'm making a list of what I'm given. I'm including what I'm trying to find. And this is very important because I have 4 equations to choose from. I got to make sure I use the right one. One way to do it is to look at what I have. I have A, I have T, I have Vi, I have delta x. Pick the equation that has A, T, Vi, delta x. A, T, Vi, delta x. Pick the equation that has those 4 things in it. The other way to choose it is to look for what it doesn't have. This list here does not have a VF in it. There is no VF. That is the equation that has no VF in it, is the no final velocity equation. So you can either look at what you have and pick the equation that has those same variables in it, or you can look at what you don't have and pick the equation that doesn't have that variable in it either. They'll both lead you to the same equation. So let's substitute. Delta x is our variable. VI is 7.1. T is 2.5. Plus 1/2, don't forget the 1/2. You could put it in as 0.5 if you want to. A is 12 meters per second squared, and T again, 2.5. T is in here twice. Now I'm going to simplify. 7.1 times 2.5 is 17.75. Meters per second times seconds would simplify down to meters because the seconds would cancel. 1/2, 12. 2.5 squared is 6.25 seconds squared. So I went ahead and squared that number. Now I'm going to get all of this multiplied out. 1/2 times 12 times 6.25. That's 37.5. Second squared in the numerator, second squared in the denominator, those cancel out, leaving us with meters. If you're ever doing one of these problems and the units don't cancel correctly, that means there's a mistake somewhere. So if you're going to ask me, do I have to put my units in there? Units are a great way to make sure that you're setting things up correctly and they're doing your math right. Because if you're not doing it right, your units won't cancel like they're supposed to. So 17.75 plus 37.5 is 55.25 meters. That's how far our car will travel as it accelerates. So again, more involved, a bit more to it than what you see in your basic kind of motion problems. Let's take a look at another example. A projectile is accelerated from rest to a velocity of 12 meters per second to a velocity. 2 indicates final. 2 tells you where I'm going. I'm going to the library. That means I'm going to end up at the library. 2 is where you end up. So that's VF. If the acceleration is 2.5 meters per second squared, let's say, how far will the projectile travel? Wait a minute. I've only got 2 numbers. All my kinematic equations have 4 variables. So I'm going to need at least 3 numbers to do my calculation. So what's missing? What's missing here is a hidden number, and it's right there. Rest. From rest implies that you started at 0 meters per second. Hidden numbers. Got to watch them in a kinematic problem. They come up all the time. We want to know how far. How far is a displacement, delta x? How far? What's the distance? What's the displacement? That all comes down to delta x. Sometimes when questions are written, whoever's writing them isn't careful and they'll put distance in there. These are all velocity based, so it's all displacement, it's all delta x. So how far, what's the distance, what's the displacement? All of those are ways of saying delta x. VF, A, VI, delta x. VF, VI, A, delta x. That's the only equation that fits those 4 variables. It's the no time equation. And if you look through the list, we don't have time. Substitute. VF is 12 meters per second squared. VI is 0 meters per second squared. And a lot of students don't write that down. And that's fine. 2 is just part of the equation. A was 2.5 meters per second squared. And delta x is our variable. I'm going to simplify all this. So I'm going to go ahead and square this, square that, multiply that. That's what I get. 12 meters per second squared would be 144 meters squared per second squared. The 0 just disappears. 2 times 2.5 is 5 meters per second squared. The 2 has no units on it, so nothing changes there. Now I got to divide both sides by 5 to solve. And when I do, 144 divided by 5 is 28.8. Meters squared per second squared, the seconds squared canceled out. That meter cancels out one of those meters, leaving us with just 1 meter as our answer. So again, different equation because we had a different set of numbers to work with. And we need to look at what we're given carefully to figure out which equation best suits our data. Let's do another one. A satellite accelerates from 30 meters per second to 120 meters per second over a time of 2.5 minutes. What's the acceleration? So again, let's start working through. From 30 meters per second, that's VI. From tells you where you start. To 120 meters per second, 2 tells you where you're going to end. That's VF. Over a time of 2.5 minutes. This is a good time for me to remind you to always watch those units. How do we make physics more challenging? By making you watch for units. Both of my velocities have seconds for time, but my time is in minutes. These units don't match. So that is going to be a problem. We got to do a conversion. 1 minute equals 60 seconds. Start with what I'm given. 2.5 minutes. Times and then a fraction bar. So you know there's a fraction bar under here. I'm starting with minutes, so I'll put the 1 minute on the bottom. I'll put the 60 seconds on top. And again, that's all for unit cancellation. I need these minutes to cancel out. The 60 is on top, so I multiply by it. 2.5 times 60 is 150. Only unit left is seconds. So now all of these things will match. I will not use that number. I'll use the 150 seconds instead. I want to know what the acceleration is, so I'm looking for A. VI, VF, TA. VI, VF, TA. VI, VF, TA. I'm going to use the first kinematic equation. That is the no delta x equation. It's the no displacement equation because I don't have displacement in my list. Substitute. VF was 120 meters per second. VI was 30 meters per second. Plus A is our variable, and T is 150 seconds. I'm going to subtract 30 meters per second from both sides first. 90 meters per second equals A times 150. Then I'm going to divide both sides by 150 seconds. And when I do, I get 0.6. Meters per second divided by seconds would be meters per second squared. So again, watch for those units. Make sure your units all match up so that your units can cancel out the way they're supposed to, or in this case, combine together the way they're supposed to. If you get to your problem and you're doing your math and the units don't cancel like they're supposed to, or they don't combine together like they're supposed to, that tells you there's something wrong with them. Either your equation's wrong and you set it up wrong, or there's a unit that needs to be converted somewhere. All right. Let's take a look at some issues, some times when we end up having to deal with negative numbers, because they will pop up. There will be some negative numbers that show up, and again, you got to remember negative just means direction. A car slows from 30, from is where we start, so that's VI, to 12, 2 tells you where you end, VF, while covering a distance of 50 meters. Distance, again, don't let that fool you. This is all velocity based. That's your delta x. What's the car's acceleration? We're looking for A. We are looking for A. Meters, 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 those all cancel. No unit conversion to do there. VI, VF, delta XA. VI, VF, delta XA. VI, VF, delta XA. We're using the fourth kinematic equation, the one with no time. Let me go back and look. We do not have time, so that's the correct equation. Substitute. 12 meters per second squared equals 30 meters per second squared plus 2 times 8 times 50. I'm going to simplify. I'll go ahead and square both of those, and I'll do the 2 times 50. That gives me this. 12 squared is 144. The unit also gets squared. 30 squared is 900. Again, the unit also gets squared. 2 times 50 is 100. No unit on the 2, so that just stays meters. I will subtract 900 from both sides, and that will give me negative 756 meters squared per second squared on this side. Don't worry about that. You're allowed to have negatives, just direction. Now divide both sides by 100 to solve. Negative 7.56 is the number. Meters squared per second squared divided by meters will eliminate one of those meters, leaving with meters per second squared. So don't be afraid of the negative numbers. This negative just means it's opposite of motion. Our object was moving to the right, positive 30, positive 12. That's the assumption we made. The acceleration is just to the left in the opposite direction of my motion, which means we're slowing down. So again, don't forget those negative signs can pop up. Do another one with a negative sign in it. A ball is rolling to the left at a rate of 13 meters per second. My VI is negative 13 meters per second. Negative because we're going to the left. If the ball accelerates at 0.75 meters per second squared, that's A. For 3.4 seconds, that's T. What will the final velocity be? I'm looking for VF. Meters, meters, seconds, 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 no units to convert there. That's all good. VI, A, T, VF. VI, A, T, and VF. VI, A, T, VF. We're using the first kinematic equation, the no displacement equation. And as you see, there's no delta x here, so that makes sense. Substitute. VF is what we're looking for. VI is negative 13. Don't forget the negative sign. Plus A is 0.75 meters per second squared, and T is 3.4 seconds. First thing I'll do is I'll simplify that. 0.75 times 3.4 is 2.55. Then negative 13 plus 2.55 is negative 10.45 meters per second. Why the negative? Because it's still moving to the left. It's still moving to the left. Why the decrease in speed? We went from 13 meters per second to 10.45 meters per second. Why the decrease in speed? Well, the velocity was negative and the acceleration was positive. They have the opposite sign, and since they have the opposite sign, that should slow down, and that's what happened. So you can be careful with signs. They're going to pop up in this. One final problem in this marathon of math. I should think it's one final one. No, two more, sorry, in this marathon of math. This one is to deal with some other issues, negative signs in this one. We have to deal with work involving time. A car moves 30 meters per second, accelerates at a rate of negative 2.5. Now, it doesn't say left or right, so we're going to go on that assumption that it's positive, just like we did back when we were using the basic equations. So VI is 30 meters per second. It accelerates at a rate of negative 5.2 meters per second squared, so that's A. And that negative sign is important. These are going to be opposite, so we should expect it to be slowing down. It covers a distance of 4.5 meters, and again, don't let distance fool you. It's delta x. It's displacement, really. This is all velocity based. How much time did it spend accelerating? We're looking for t. Now here's the first thing, and it's going to carry over into the next one too because it's that important. VI A delta xt. Go back to our equations. VI A delta xt. You would think that would be the equation to use. And if you want to do some pretty serious math, you can. But the problem with using this to solve for t is that it's in here twice. And the first time it's not squared, and the second time it is. So if you know how to do the math to solve that for t, you go ahead and substitute and solve that for t. But that's going to take a while, and it is some pretty challenging math. So what I would suggest is you don't use that equation at all. Forget it. Never use this equation to solve for t ever, 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 ever. Just don't do it. So what are you going to do instead? Well, I have enough information here with the VIA and the delta x. The VI, the A, and the delta x. I have enough information there to find a final velocity. And once I find the final velocity, I actually have two equations then I can use to find t. I can use either one of those to figure out what the time is. So my suggestion, never, ever, ever use delta x equals VIT plus 1/2 AT squared to find the time. Start by finding the final velocity. VF squared equals VI squared plus 2A delta x. That's the equation you want to use. Substitute. VI is 20. A is negative 5.2. And delta x is 4.5. Simplify. 20 meters per second squared is 400 meters squared per second squared. 2 times negative 5.2 times 4.5 is negative 46.8, and it would be meters squared per second squared because we have meters per second squared times meters. The meters will square up there. Add those together, and then square root both sides. That's your final velocity. Now, like I said, once you've got your final velocity, you can use either one of the first two kinematic equations to solve for t. I like this one because it's simpler. So that's the one I'm going to use. VF is my newly calculated number, 18.8. VI is still 30, right from my list. A is still negative 5.2, right from my list. I'll subtract 30 from both sides, and I'll end up with negative 12 over here. And I'll divide both sides by negative 5.2. Make me 2.3. Meters per second divided by meters per second squared. The meters cancel out. One of the seconds cancel out. The seconds in the denominator of the denominator, so it moves up. And you end up with 2.3 seconds. So again, don't ever use delta x equals VIT plus 1/2 AT squared when you're trying to solve one of these, unless you want to do a lot of math. Find the VF first. It usually can be done in a minute or less. And then use that first kinematic equation to find your time. Now, why did I throw this one in here? It's going to be very similar. We're looking for some stuff in final velocity, just like we did in the first part of that last one. But I want to point something out to you that does happen, that does sometimes mess up students. So if it messes people up, it's worth talking about. A boat in the water is traveling with a velocity of 12 meters per second. We're going to say that's VI because that's what it is doing. The boat accelerates at a rate of negative 2.1 meters per second squared. So that's acceleration. For 10 seconds. That's time. What's the final velocity? So I made this a little easier instead of asking you anything about time. We're not going to have to worry about that 1/2 AT squared thing. But what we got here is a situation that often messes students up because we're going to end up with a negative velocity. Let me show you how it works. VI, AT, delta F, without going back to the list, that's the equation that we used. It was the first equation we used in the last problem. Substitute. VF equals 12 meters per second plus negative 2.1 meters per second squared times 10. Simplify. Negative 2.1 times 10 is negative 21. And solve. 12 plus negative 21 is negative 9 meters per second. Now this, again, will confuse students when they see this. I had a positive velocity, I ended with a negative velocity. How and why did that happen? And the answer is pretty simple. This is a boat. It's moving along to the right, and we put the engine in reverse to the left. It slows down, slows down, slows down, comes to a stop, but the engine is still going to the left. So the boat's going to start moving to the left. And that's what that negative sign tells you. So again, signs come up with this. Try not to let them throw you. And if you've made it to the end of this marathon video, my hat's off to you.